Okay, so far we've looked at graphing a parabola and finding its vertex and all that kind of stuff, but who really cares about that? How can we use that in real life situations? Well, one way that we can use it is an idea called optimization. Optimization is setting things up in such a way that something is optimized or the best possible result of your setup. Okay? So for example, we're going to maximize area in this first example. So a nice boy has 24 meters of fencing. He wants to build a rectangular enclosure for his dog with a maximum possible area. Okay, so we could certainly figure this one out without quadratics and parabolas, but what we're doing is making a connection between that shape that we can graph and this situation that we want to find the optimal area for. Okay, so let's start by just drawing a particular shape. So let's say that he wanted to draw like a really long rectangle like that. Okay, so 24 meters of fencing is what's used. So let's say on the edge here, let's go move this over. Let's say on the edge, we wanted to make this 1 meter. All right, so far then, in the rectangle, 1 meter per side means 2 meters has been used up of fencing. 24 meters is what we have to work with at the very beginning. So 24 minus the 2 meters that we've used up leaves us 22 meters. And we're going to split that 22 meters up into 11 here and 11 here. So 11 plus 11 plus 1 plus 1 gives us the 24. All right, so putting that into our chart, we have a rectangle of 1 meter, a length of 11 meters, and at this point here, let's just recognize we're trying to maximize the area. So how do we find area? Well, area of a rectangle is just width times length. All right, so we can easily find the area by going 1 meter times 11 meters is, well, 1 times 11 is 11. Meters times meters is meters squared. So there's our first rectangle. Okay, so that's not great. I mean, the dog can run back and forth, and maybe that's good. But let's check it out. Or let's draw a second thing where it's a little bit wider but a little bit longer. All right. Let's see if I can do this here. Can I move that guy around? 1 second here. Oh, well, I'll just leave it there. Okay, so let's say we wanted to make, in this second rectangle, 2 meters on the side. All right, 2 meters and 2 meters. Well, that's 4 meters of fencing. 24 meters is all we have to work with. So if we take away the 4 that we used, we have 20 left over to be split amongst the two sides. So this is 10 up here and 10 down there. 10 plus 10 plus 2 plus 2 is 24. All right, so looking at our width of 2, our length of 10, 20 meters squared. So just by changing the dimensions of this rectangle a little bit, we're still only using 24 meters of fencing, but the areas of the two rectangles are quite different. So one thing at this point we don't want to have to draw every triangle or every rectangle, but we might notice that, you know, if you go halfway around a rectangle, that should be equal to half the perimeter. So halfway around should be equal to 12 meters. So you can see that's the case, right? 1 plus 11 is 12. In the next rectangle, 2 meters plus 11 meters represents half the perimeter. So again, that's 12 meters. So we don't have to keep drawing rectangles. All we have to do is look for different combinations of widths and lengths that add up to 12. But just to do one more here, let's draw the next one in this little set, which would be 3 meters on a side 3 meters on a side. Now, we know that this width of 3 plus this length have to add up to 12 to be half the perimeter. Have to add up to 12. So, how do we figure out the other side? Well, 12. So, I know that you guys can figure this out here. I just want to link this to the algebra, what we're going to be doing pretty soon. We have 12 meters that we want the width and the length to add up to. So if I go 12 minus the width, what's left over is 9 meters for that top section. Okay, so I subtract it from 12. All right, so let's put that in here. So this is C, 3 meters times 9 meters, 27 meters. So that's even better, so the dog's happier. All right, now that we've kind of got the pattern here, we don't have to keep drawing rectangles, so let's just kind of go, well, if this is 4 meters, it has to be adding up to 12. So 12 minus 4 is 8. Area is 32. Even better. 5 meters. 12 minus 5 is 7. 35 meters. Okay, that's a little bit better. It's starting to kind of level off a little bit. 6 meters. 12 minus 6 is 6. So we have a square. Now a square is technically a rectangle, because all you got to do to be a rectangle is have opposite sides of equal length and right angles, and a square fits the bill. So 6 times 6 is 36. Okay, let's go to 7. 12 minus 7 is 5 meters. So you can see we've already covered this one. We're going back down again. So all the numbers went up, got to a peak of 36, and now they're starting to go down again. All right, so we'll leave that chart as it is, but let's just remember that what we're kind of doing here is when we have the width, remember the way to find the length is to go 12 minus whatever the width is, and that leaves us what the length will be. All right, so next thing what we're going to do here is just sort of see what shape this makes. I'm sure you can probably guess what it's going to be. Is let's put those sort of points on this graph and see what we get. So what we're going to do is we're going to let x be the width and y be the area. Okay, so I'm going to graph the points. When the width is 1, the area is 11. When the width is 2, the area is 20. When the width is 3, the area is 27, and so on. Okay, so I'm going to graph all those points. All right, so down here, width would be the x variable. 1, 2, 3, 4, 5, and so on. I'm just going to pause the video and do that. All right, so here we are. I've put my numbers on here. So again, when I label the x and the y axes, the width is in meters, the area is in meters squared. All right, I decided to go up by 2's so that I could go all the way up to 36 and so on. All right, so let's graph these things. So when the width was 1, the area was 11. When the width was 2, the area was 20. 3, the area was 27. When it was 4, the area was 32. When it was 5, the area was 35, so 5 comma 35. When it was 6, the area was 36. After that, it started going down. When the area is 7, the area is back down to 35. Well, you can see that the shape that we're drawing here is a parabola. So, you know, when the width was 8, that's going to be just like the other triangle, or I keep saying triangle, the other rectangle that was 4 by 8. Well, this is 8 by 4, so these are the same. So we can just, by symmetry, keep going down. Alrighty. And, you know, the maximum width that you could have is 12, okay? Because if you think if you had a rectangle that was, let's say, 12 here, I know this is not a scale. well, then this would be 0, right? Because that's using all the fence. So this would be like actually like a complete flat rectangle. You couldn't even draw it. So we can see that when the width is 12, the length would be 0, and you'd have an area of 0. So 12 comma 0 would be where that parabola would be. Okay, so where that point would be, rather. So here we can see we've got this parabola shape, and first of all, I'm going to connect all the dots, because even though we didn't do it, it is possible for me to, it's all possible for us to have, let's say, had a width of 1.5 or something, you know what I mean? Like, I'm not sure if that's exactly where it would fit, but it's possible to have us have widths that aren't exact numbers of meters. So we can draw this continuous graph. But the thing is, we can see that the maximum area occurs at the vertex of this parabola that is upside down, which, you know, we saw from the chart, but we're also seeing, you know, shape-wise. So we can see the maximum area occurs at this point. This point is 6, 36. So 6, the x-coordinate, well, x stood for width, so that's the best width to do. 36 was the y-coordinate, that stood for area, so that's the best area you can get. Okay? So the maximum of this parabola, or the vertex of this parabola, is like the best situation. So according to this, we want to make a rectangle that's 6 meters by 6 meters, because the width is 6, well, the length is 2, and that will give us a max area possible of 36 meters squared. Okay, so yeah, I think that's all I really need to say about that. The one thing I notice here is that it's good to recognize that a reasonable domain for this would be, well, the lowest width you would want to ever do would be 0, and the highest width that you would ever be able to do is 12. So the domain for this parabola would be 0 to 12, written in interval notation. Okay, just that little section there. Why am I bringing that up? Well, we know that the parabola would continue going on. Over here, it would be going into the negative x zone, and over on the right side, we could say that the parabola continues past 12, but in this situation, that wouldn't make sense to have negative areas or negative widths, so let's take that left side away. And it wouldn't make sense to have widths that are bigger than 12, because then we just couldn't make a rectangle. All right, so what we've done here is we've sort of associated the idea of parabola with maximizing or optimizing something. So on the next page, let's look at how we can do that maybe without the graph. All right, so here we're going to write a function to represent the rectangular area of the enclosure and give the standard and vertex form of the function. So we want to maximize area. All right, so we'll just keep that in mind. All right, so let's draw ourselves a rectangle, and this time without sort of having a particular length and width, let's just say, let's call this width x, and the length up here. How can we use the variable x to describe that length? Well, we kind of already said before that if you have the width, you can get the length by subtracting from 12, because those have to add up to 12. So the length here would be 12 minus x. All right, so when you're maximizing, when you recognize what you want to maximize the area, okay, when you decide what that is, that's going to be your y. So let's set this up.
Good morning, everybody. Today is the Feast of the Guardian Angel.
Okay, I gotta figure out where I was here. All right, so we are doing the area of this rectangle, so area is equal to width times length. So area, we're gonna represent with y. thing that we're maximizing. Width is x, and that's a multiplication up there. And width is, why was not the drawing? Try that again. Width is 12 minus x. Okay, so when we set it up that way, let's expand this out here. So y is equal to x times 12 is 12x minus x squared, which is negative x squared plus 12. Well, you can see this is a upside down parabola, which is exactly what we got on the previous page. Oops, I forgot the 12x. There you go. Negative x squared plus 12x is the parabola that we just had on the previous page. And yeah, so we don't have to necessarily graph it. We can just figure out the maximum by finding the vertex, right? Because if we go back, really, once we have that parabola in equation form, what we're interested in is where is that vertex occurring, okay? All right, so where is this vertex occurring here? Let's use our P and Q formulas to determine that. So P is negative B over 2A, all right? So P is negative 12 over 2 times negative 1. P is equal to negative 12 over negative 2, which is 6. So right away there, we can see that the best width to have, right, because x is width, the best width to have is 6 meters. Now let's figure out what the Q is. Q is C minus AP squared. It's important to note here then that C is 0, right? So let's plug in what we have. Q is equal to C minus A P squared. Now P is 6. So it's Q is equal to 0 minus negative 1 times 36, which is 0 minus negative 36, which is 36. Okay? Now the Q is the y coordinate of the vertex. Y is area. So this is the best area. Okay? So up here we'll say that the vertex of 6, 36, right? The meaning it has in this question is that's the best width, right, x, and this is the best area, y, okay, where area is maximized. All right, so what dimensions of the enclosure will give the maximum area? So notice here it's saying what dimensions. So we have to go that little step further and say, well, the width is 6 meters and the length, right, the other dimension, well, we know that if one side's 6, the other side 12 minus 6 is also 6. Okay? So on the next page, you guys have some questions here where you have to go through and maximize the area of the particular things that are done. Now, I know you can do these without using algebra, but just to sort of understand the process of setting up a sort of a formula that turns into a parabola, find the maximum or the minimum or whatever is being needed here, and kind of doing it that way algebraically. Okay? I will mention as well that some of these things only have one wall is kind of like up against something. So it says a rectangular area is to be fenced using the wall of the barn as one side. So just because I know it's might be a little bit confusing, is if you have a barn there, and this is viewed from the sky, looking down on the situation. So there's the barn. Okay. This thing here is this rectangular enclosure is built against the barn, so it'd be like that. So you can use all your fence up just on those 3 sides of this rectangle, okay, because the barn's acting as one of the sides. All right, so good luck. See ya.